Hey everyone, welcome to The Explainer. I am incredibly excited to be your guide today as we unlock a mathematical mystery that is literally shaping the universe around us. Seriously, whether you're a student sitting in a classroom in Tokyo, studying at a cafe in London, or just taking notes at home in Buenos Aires, this explainer is built to give you a crystal clear, colorful breakdown of a massive foundational physics concept. We're talking about the hidden mathematical language that connects some of the most high-stakes, thrilling careers on the planet.
Think about it. Whether it's physicists mapping out the cosmos, air traffic controllers preventing multi-ton jets from colliding in the sky, or the video game creators designing the incredibly immersive digital worlds you play in every single day. On the surface, these jobs seem completely different, right? But they actually share a really strict foundational reliance on just one mathematical tool. They all rely heavily on vectors.
Okay, let's dive into this, because this is the central question of our explainer today. You hear the word thrown around all the time in sci-fi movies and high school math classes. But what exactly are vectors? And more importantly, why do they matter so much to how we understand and manipulate the physical world? Well, to unlock that answer, we first need to take a quick step back and look at how we measure anything at all. All right, section 1, magnitude versus direction. Let's look at the basic building blocks.
Let's start with the absolute simplest form of measurement. A scalar is a quantity that only has magnitude. And hey, magnitude is really just a fancy scientific word for how much. Think about your everyday life. The distance between you and that park bench outside your window, that's a scalar. The volume of the coffee in your mug, or its temperature, those are scalars too. They just tell you an amount. 50 feet, 8 ounces, 100 degrees. Easy, right? But here is where it gets really fascinating. A vector is a quantity that possesses both a magnitude, the how much, and an absolutely crucial extra piece of information, direction. It's the how much paired directly with the which way. Adding that extra dimension completely transforms a simple measurement into a super powerful directional tool.
To really cement this idea, let's think about that park bench again. If I tell you it's 50 feet away, that's your distance, a scalar. But if you actually want to navigate to that bench, knowing it's 50 feet away just isn't enough information. I mean, it could be 50 feet behind you, 50 feet above you, or straight ahead. You need what we call displacement. You need to know that it is exactly 50 feet north. That combination of distance and a specific direction, that is your vector.
Moving right along to section 2, the tent moving experiment. Let's explore coordinate invariance.
Now, what's really interesting about this is that vectors do not change based on your perspective. They remain invariant to the coordinate system. To picture this, imagine a bright, colorful camping tent. You and a friend need to move this tent across a campground. You stand on opposite sides of the tent to pick it up, which naturally means you're facing completely opposite directions.
Picture this in your head. From your friend's perspective, they move 2 steps to the right and 3 steps forward. But to keep the tent perfectly steady, you, since you're facing the opposite way, have to move 2 steps to your left and 3 steps backward. If you just read those instructions out loud, they sound totally contradictory. From a personal perspective, you two are doing completely different things.
But here is the brilliant twist.
Despite those seemingly opposite physical movements, you and your friend both ended up moving the tent the exact same distance in the exact same absolute direction across the campground. You both followed the exact same vector. No matter which way you were facing, the underlying vector itself didn't change at all. That is coordinate invariance in action. Section 3, the language of coordinates. Let's see how this works mathematically.
To put this on paper, we need a coordinate basis. This just consists of the directions, like your classic X and Y axes on a piece of graphing paper that we use to describe everything we chart. It's basically the essential starting point for describing movement from an origin point to a brand new destination. If we compare those two tent-moving perspectives side by side, we see something super interesting. For your friend, whose basis is standard X and Y, their mathematical movement expression is 2X plus 3Y. We call this an array. But for you, since you're facing the other way, your coordinate basis points in the opposite direction. Let's call them X prime and Y prime. So your movement creates an entirely opposing array. Your differing physical perspectives created completely different mathematical arrays.
But wait, there's a catch here. An array alone does not completely describe a vector. Just looking at a string of numbers isn't enough. By themselves, those numbers are kind of naked. They desperately need context to mean anything in the real physical world. And this brilliantly illustrates a core rule. An array only acquires meaning as a vector when it is assigned a coordinate basis. The numbers only reveal the true vector when you pair them up with the specific perspective, the basis they were recorded from. It's actually a fascinating concept that maps perfectly onto something we use every single day: language. Think about it like this. The individual numbers in an array are exactly like individual letters of the alphabet. A random sequence of letters only becomes a meaningful word when you apply the specific rules of language. In the exact same way, a mathematical array only becomes a meaningful vector when you apply a coordinate basis. Different words in two languages, like dog and parrot, convey the exact same animal. Different arrays from two bases describe the exact same physical vector. Pretty cool, right? Let's move to section 4. Enter the tensor family. Time to move beyond vectors. So this brings us to a really exciting question. We know scalars give us an amount. Vectors give us amount plus direction. But can anything convey more information than a vector? Is there another, more complex level to this mathematical hierarchy? The answer is an enthusiastic, absolute yes. Let's say you're a developer designing a video game, and you want to model incredibly realistic, dynamic water physics. To pull that off, you need something called stress, which is a second-order tensor. This is a physical quantity where a force, which, remember, is already a vector, is combined with yet another vector that provides orientation. Imagine the water in your game engine. You can have the exact same force magnitude, pushing in the exact same direction, but depending entirely on how that force is oriented against the surface of the water, you might create gentle rolling ocean waves, or you might create violent spinning whirlpools. That added layer of orientation data, that's exactly what makes it a second-order tensor. And guys, mastering this theory isn't just about passing your physics exams. There is a huge, tangible reward here. Tensors are literally the mathematical backbone of our modern world. They're used in cutting-edge scientific simulations, aerodynamic car designs, life-saving brain imaging tech, and yes, those mind-blowing video game physics we all love. Mastering vectors and tensors means mastering the tools used to build the future. So, let's wrap up our journey today. Scalars, vectors, and the tensor family provide us with an incredibly elegant way to make sense of complex physical interactions. We went all the way from measuring the simple temperature of a cup of coffee right up to mapping coordinate invariant forces in 3D space. It just highlights the sheer beauty and the fundamental usefulness of mathematics. Which leaves me with one final provocative thought for you today. The tools are right there in front of you. You've got the vocabulary down. So how are you going to use the elegant language of mathematics to decode the complex universe around you? Keep questioning, keep learning, and I literally cannot wait to guide you through our next explainer. See you then.